So what are the alphas and betas look like? The alphas and betas are voltage dependent. And so rather than going through all of them, they're on the handout for the homework. They're in the lecture notes, but we'll just look at one of them. Alpha m as a function of voltage is not a function of time. Alpha m is only a function of the voltage. It's equal to minus 0.1 times v plus 35 over e to the negative 1 times v plus 35 minus 1. And beta m v is equal to 4 times e to the negative v minus 60 over 18. So if we were to plot this as a function of voltage, let's set 0 here. This is ENA, this is EK here. And we plot BM. BM starts off at negative voltages, very large, and alpha m goes up like this. And when you add them together, when we calculate n infinity, so sorry, this is beta m as a function of voltage. This is alpha m as a function of voltage. When you calculate, this is alpha over alpha plus beta, which is equal to m infinity. I should have done that in a different color, right? And if I plot something like this is 1 over alpha plus beta, which is equal to tau m. So it shows us if our voltage is really close to the potassium reversal potential, the channels are closed, right? The n infinity is closed. The time constant is fairly large. It's slow. As we get closer to the voltage, the threshold, what happens is the potassium channels start to open up, right? They want to go to the open state and infinity, but the time to get there is slow. It takes a long time to get there. Once the voltage gets really high, like at the peak of the action potential, they really want to get up there. They're all going to be open, and the time to get there is going to be fairly short. So they're going to start opening up. So if we plot, I'm not going to plot the curves for all of these, but if we plot, this is the n infinity. That's the sodium activation curve. Sorry, this is 0 millivolts. This is ENA. And this is EK. And this is E rest. We'll find that the M infinity, goes from 0 to 1. So that the activations, the inactivations only are between 0 and 1. They do not go greater than that. This is one way you can test your code to see if it's correct or not. If you plot out M infinity as a function of voltage and it goes beyond 1 or less than 0, you know something is wrong with your equations, with your code, not with the equations. And then the other thing is the sodium inactivation. And so this is the H infinity. Looks like that. And so here we're sitting at rest. If we push up here, then suddenly we're going to get the sodium channels opening. That's going to bring us up here. Then the potassium, the inactivation starts to come in. The sodium current goes down to 0. Then the potassium current gets open, bring us back down to the E rest, to the E potassium. And then the potassium channels close, right? And then it comes back to E rest. That make sense? And if we plot taus, this is the time constant as a function. So this is ion infinity. This is tau of the ion. We'll find that the time constants of the sodium, this one of these guys are the This is N, H, infinity. You know, they look similar. What's important is the M, infinity. This is the sodium activation is orders of magnitude faster than the sodium inactivation and the potassium activation. So when the sodium channels open up, they open up and the current gets big very, very quickly. Then the potassium channels start to open and the sodium channel inactivation catches up. The sodium channel current turns off and the potassium current goes up. So it goes fast, slow. As we get up to close to the peak of the action potential, everything starts to move very fast. And the action potential shuts off. The width of the action potential is about 1 millisecond. When the sodium the inactivation, what happens when the voltage comes back down, sorry, this is the sodium, this is N inf, and this is, I should draw different colors, right? This is so this is H inf, and this is N inf, right? So the sodium comes back down, and then the inactivation drops, turning off the action potential, and then slowly recovers. The activation recovers fairly quickly, right? So if you were to go stimulate a neuron again right here, you'll find that a lot of the sodium channels are inactivated. And so it's not really ideal. And so it turns out that if you try to make an action potential right here, you're not going to get an action potential. And at some point here, there's so many sodium channels inactivated that no matter how much current you put into it, you can't get it to fire an action potential. And this is what's called the absolute refractory period. And then there's a period of time when you take more current to make the neuron fire, and this is called the relative. So this is absolute refractory period is equal to no stim equals action potential, and then this is larger stim results in action potential. Okay? So that's the Hodgkin-Huxley equations.